Okay, so let us start today's class. Okay, so we had started a little bit on the MM1KQ in the last class, and then we had to find out or derive the various values that we were looking for in a queue in an M for an MM1Q, MM1KQ. So as you can see that the one thing that changes here than the MM1Q is that there is a fixed size of the system. That means the system capacity is fixed here and that is given as K. So as per definition of system capacity, we know that it is defined as the total number of jobs that can be there in the system, including the one which is getting served at the server. Okay. So here you have one server. So one guy is getting served at the server at a time. So therefore your buffer size can be K minus 1 and one guy can be served at the server. Okay. So you have a total system capacity of K and rest are same as, we already know from our Kendall notation. We have MM1 Q here with K system capacity. Population size is also infinite and the jobs are being scheduled as per FCFS. So what will happen if the arrival rate is too high? Okay, so that's what is given here. So if lambda is too high, which happens in a very realistic scenario, that of course we will most of the times we will have a fixed capacity of the system or a fixed buffer size. So in that case, what we will have to do that whenever the arrival rate becomes too high, then the packets will get dropped. Okay, so buffer overflow condition will happen at that time. Now, how will we analyze such a system? So we have to just analyze with whatever is actually getting into the system, right? So therefore, we first find out what is the probability of blocking, okay, or blocking probability, which is defined as the probability that an arriving packet will find the queue to be full, okay, or the buffer to be full. Because if only if it finds the buffer to be full, then only it will be dropped. Okay, so that's the probability of blocking. Now, so how do we find out that effectively how many packets are actually arriving into your system, your queue that you have? So for that, we try to find out this value using this, that is effective arrival rate. Okay, so you know that what is the probability of blocking. Okay, so how will you find out the effective arrival rate? That is found out by this, that is summation over n equals 0 to k minus 1 lambda pn. Okay, so that is nothing but it is equal to lambda times 1 minus pk. Okay, so this is your effective arrival rate that you have. Now when we will work with this system, we will work with the effective arrival rate, because you know that effectively among all the jobs that are arriving, effectively these many jobs will be entering your system on an average. Okay, so this is your effective arrival rate. Now let me get to the next part. So how do we look at such a system? Okay, so this is the state transition diagram. So you have whenever there is an arrival, you go to the next state. Whenever there is a departure, you go to the previous state, just like the same birthday process that we were having. Only problem is it will work up to the kth state, right? After the kth state, that means up to k jobs that can be there in the system. Whenever there is more than k jobs that are arriving, it will not be able to enter the system at all. Okay, so that is why it is given like this here. So that is undefined here, because after the system, the number of jobs in the system is k. After that, it will not grow more because the buffer capacity becomes full at that time. Okay, so now let's get to the derivation parts. So this is the probability of blocking. Okay, So we have already defined probability of blocking as the probability that an arriving packet will find the queue to be full. Okay. So this is given by, so I hope that you have read Raj Jain's book by now. Um, so the blocking probability is basically given by 1 minus rho times rho power k divided by 1 minus rho power k plus 1. Okay, k being the system capacity that has been already been given you. And of course, rho should not be equal to 1. Okay, but now let's get to the other point, that is, E of n, E of t, E n q and EW. These are the values that we generally um, try to find out. Okay, so just hold on a second. Yeah, just a second. Okay, so E of n is actually the total number of jobs, the total number of jobs that are in the system. Okay, that is E of n. Okay, so that is equal to rho by 1 minus rho minus k plus 1 times rho power k plus 1 by 1 minus rho power k plus 1. It would seem to you like, it is, I'm just going on with the formulations here. But fact is that if we try to derive all of them, it is going to take really long time and it is going to become too complex for the current amount of, studies that we have done so far. Okay, so it will be full probabilistic analysis and it will become too difficult, and some feedback I have got is like probabilistic analysis is becoming a little difficult and all that. So I'm just telling the formulation here. Okay, just keep these in mind. So from E of n you can get E of t from Little's law, that is E of n divided by the effective arrival rate. Okay, so that will be lambda times 1 minus pk, that is the effective arrival rate. Okay. Then you get again E of nq is equal to rho by 1 minus rho minus 1 plus k times rho power k by 1 minus rho power k plus 1 times p. So this is whole times p. Then sorry, times rho, not p. Then we have E of w that we can get from E of t minus 1 upon mu, right? So that comes out as, this is also you can get like E of nq divided by lambda times 1 minus pk. Okay, so this is what we get from the mm1kq. Now we do have an example to do here, but I think I'll skip this for now. I will do it later on. I'll first go through the other queues. Okay, so let's get to the other queue, that is having m servers. Okay, so you do not have any limitations on the system capacity or on the population size or the scheduling discipline. It is same as an MM1 queue, except that you have m servers. Is the network not working? Okay, can you guys hear me?
Yes, ma'am, now we can hear you.
Okay. Hmm. So I was talking about MMMQ, right? So it is same as an MM1 queue, except that you have M servers, except unlike MM1 queues, one server. Okay, so you just have M servers here. All other things are same as an MM1 queue. Okay, so that means inter-arrival distribution, time distribution is exponential distribution, and service time distribution is also exponentially distributed. Okay, and you have m number of servers. So please remember the properties that we had read in queues. Okay, so these servers have to have the same rate of service. Okay, that means the server should have, all of these servers should have the same features, same properties, otherwise it will be considered as a separate queue. Okay, so this is the way the server, the MMM queue works, and the M servers are here. So now there will be arrivals, and all of these arrivals can go to any one of these M servers to be served, right? This is exactly the same as you will see in a boarding pass counter in your airports. Okay, so you have one line, and from there you have like several counters, 6 or 7 counters, or maybe 3 or 4 counters depending on the airport. And then the passengers will be taking whichever survey, whichever counter is free, they will be going to that counter for getting their boarding pass, right? So you can imagine that kind of system like this. Okay, so this is an MMM queue. Now this is how its state transition diagram looks like. Okay, same as a birth death process. All right, so now you will have the system like this. See, you have one arrival and one departure. So if you have one arrival from the 0th state, you will go to state 1 with one number of job in the system. And if you have a departure from there, then it will be mu, and then you go to the 0th state. Okay, but now if you want to have like 2 jobs in the system, okay, so again from the state 1, with one arrival only you will get to the state with 2 jobs. Okay, because that is happening like one by one, one after the other. But if there are 2 jobs, okay, so then what will happen, that you have 2 servers here, or sorry, you have m number of servers here. So you have 2 jobs in the system, so there's 2 mu, twice of mu you get to the um, first state, and then you get to, then one more mu is gone, that means one more departure is there, and then you get to the 0th state. So like that, you get one arrival, you go to the next state, and then this leads to you leads you to the previous state, the thrice of mu here. So now like this you go on and go on, so on and so forth. So once you have like uh, m jobs in the system, remember you have m servers, so at a time only m jobs can be handled. So with m you can depart, like m mu is able to depart from that system. But when it comes to this scenario where you have m plus 1 jobs in the system, that means those other jobs will be getting queued. So you will only be able to depart only mu jobs from the system. Okay, so that is why it is mu even after the state m. All right, so that is the state transition diagram that you are having for MMMQ. Now let's get to the derivations for MMMQ. So now you have M servers in this system. So how do we find the service utilization or server utilization? Okay, so that is rho, and that will be given by lambda by m mu, given that you have m servers. Okay, so P0 is defined as the probability that there are no packets in the system, that is all the servers are idle. Okay, so this is given by P0 is equal to summation of I equals 0 to m minus 1 m rho to the power I by I factorial plus m rho power m divided by m factorial times 1 minus rho. This is power 1 minus 1. Okay, then also you have to find out that even though you have m servers, what is the probability that your job will be queued? Okay, so that is given by probability of queuing, which is denoted here as zeta, and zeta is equal to m rho power m divided by m factorial times 1 minus rho times p0. Okay, so this is your probability of queuing. Now From here we get the different values, that is E of NQ, which is given by rho zeta divided by 1 minus rho. You have E of N, that is equal to lambda times E of T from your Little's law. E of T we can find out from EW plus 1 upon mu, and EW you can find out from Little's law using E of NQ divided by lambda. Okay, so these are the different values that you get. Now we'll get to one more variation of a Q, that is MMMQ. MMMM, 4Ms. Okay, so 4Ms, first two will denote that arrival time distribution, inter-arrival time distribution is exponential. Second one denotes that service time distribution is exponential. Third M denotes that there are M servers, and fourth M denotes that the system capacity is also M. That means your system can handle only as many jobs in the system as you have the number of servers. Okay, so that is this kind of a system. Now of course we need a stability condition for a queue, so here our stability condition would be lambda is less than m mu, right? So since we do not have any queuing in such a system, okay, now here it is given as, and I'm also saying that we do not have any queuing in such a system. Can anyone tell me why there wouldn't be a queuing in such a system? Do you have any answer to this question? Just think about it. We have it's there in the notation itself. We have MMMMQ. So why wouldn't there be any queuing in such a system, or will there be any queuing in such a system?
The maximum number of jobs that can be handled is equal to the number of servers.
Yes,
So
so there will not be any. Yeah. So that is the reason that there will not be any queuing in such a system. So your E of T, that is the total amount of time that a job spends in your in your system, will be equal to the service time, right? So that is equal to 1 upon mu. And since there is no queuing, so no time spent in the queue. So that is, so the time spent by the job in the queue is phi, or 0 you can say, and E of n, which is the total number of jobs in the system that you can get from Little's law that we have, and that is here given by lambda times, lambda times 1 minus pk. So here also we are using the effective arrival rate. Okay, because you have a fixed system capacity, so you use the effective arrival rate times the e of t from Little's law. So e of t is 1 upon mu here, so that is 1 upon mu. Now e of nq will also be equal to phi, because there is no queuing in such a system. Okay, so that is for MMMQ. All right, now let's get to the other parts. Okay, so let's get to bufferless switch. Okay, so we have already done the bufferless switch part. We have got the theoretical utilization of a bufferless switch part as 68%. Okay, so you have input ports and output ports, and there's no buffer in those ports. Okay, so we already saw this. Now let me just see once. We have done this part already, so I will not go through this part once more. This is sorry, it is not 68%. I was telling wrong. It is 63%. Okay, I missed it. Okay, so it is 63% utilization. We have already done it in the class in the before starting the queuing theory part. Okay, so now we are going to do input queuing. So when I had started with this portion of queuing theory, or this part of queuing theory, then I had told you that I will start with I'm doing this because I want to find out, or I want to analyze what happens in a situation when you have a switch fabric with input ports and buffers. And before you guys ask me questions on, why we are not doing numericals on MM1 BQ and MMMQ, I think I will take a small tutorial class where, we will do some more numericals on queuing theory. Okay, but because we have very fixed amount of time for the course syllabus, so the class I will take to finish the syllabus first. Okay, so maybe we will have some extra tutorial class once where I will take numericals on queuing theory. Okay, so I think that will be helpful for you guys also for your exam purpose. Now let me start with the input queuing part. So this is the system. I hope that you are very much aware of this one. So these are the three different modules that are related to the PHY, MAC and network layer modalities or network layer functionalities. And everything that happens in these ports depends on the line card speed of the input port. Okay. So we have a buffer also here where all of these jobs that are entering or packets that are entering into this port, they will be waiting until they can be moved to their corresponding output port, okay, via the switch fabric. Okay, so here we have buffers only at the input ports. We do not have buffers at the output ports. All right. Now let us do the analysis of such a system. Okay, so before we do some analysis, we generally get to the assumptions part first. So let us start with the assumptions. We have n input and output ports. As the previous analysis, here too the time is slotted. Okay, we have divided the time into slots, and one packet can be sent in one time slot. We have a fixed packet length, so one packet will be sent in one time slot, and in every time slot every input generates a packet. Okay, so there's no case where there is an input port and it is not having a packet to be transferred. Okay, so you have at every time slot you have some packets at the input port. Okay, so now the destination of a packet is chosen uniformly between 1 to n. Okay, the output port numbers which are there in we have 1 to n as input port and output port numbers, so the destination will be chosen randomly from this uniform distribution 1 to n. So now in every slot n packets are generated, and we denote the average number of packets transmitted per slot as f. Okay, so f can have values between 1 to n, right, depending upon where your packets are actually getting destined to. Okay, so f will denote the average number of packets transmitted per slot. F can take values between 1 to n. Now of course there will be some packets which will not be selected for transmission because of contention, right, because we are choosing the output ports randomly. Okay, so therefore there can be situations where they are not getting the corresponding output port. Okay, so those packets which are not getting selected for transmission due to output port contention, those are defined by, or those are denoted by bi. Okay, so bi denotes the packets that are destined for output port I in a slot that were not selected for transmission due to output contention. So what will be the value of f then? F can take a maximum of n value. Okay, so f will be equal to n minus summation of I equals 1 to n bi in a given slot. Okay, so in a given slot we have this value. Now what is the average value of f? Okay, so E of f, that is the expected value, you can find out from this, that is n minus summation of I equals 1 to n EBI. So that is the expected value of f. Now BIs are IID random variables. So with that, what can we see? That with large T, when the time span that you are looking for, for that means when you look at this system for a really long time, all the output ports will start behaving identically. Okay. So when this happens, you can write E of f is equal to n minus n times EBI. Okay, so that means, so these are nothing but, in steady state, this is going to happen. Okay, so E of f is equal to n minus n times EBI, which is equal to n times 1 minus EBI. Okay, so that is the value for E of f for you. Now, our essential idea is to find out the switch capacity, right? So let gamma 0 denote the switch throughput per slot, which is given by or which will have a value between 0 to 1. Okay, so that is the switch throughput per slot. So gamma 0 will be defined as the fraction of packets that can be successfully sent in every slot. Okay, so gamma 0 is the fraction of packets that you successfully sent in every slot. So therefore it will have some relation with E of f, right? So what is that relation? That relation is given by E of f is equal to n times gamma 0. You have n ports, so n times of gamma 0. So now you can equate these two equations, equation 6 and 7. So from this you will get n times 1 minus EBI is equal to n times gamma 0. So now you will get gamma 0 equals to 1 minus EBI, or EBI is equal to 1 minus gamma 0. Okay, so gamma 0 is also your average link utilization for all output links. Okay, so now we are making some assumptions here. Okay, what are the assumptions? What are the assumptions that we are thinking of? That, it can be assumed that all the packets that are in the head of the line of input ports, which are destined to the same output port, they form a queue. Okay, so if you want some visual representation of what I'm trying to say, let me just show you. Hmm. Is the word file visible to everybody?
Yes, ma'am.
Okay. All right. So here what is happening essentially, that so now you have input ports with buffers. I'm just drawing 3 only. So 1, 2, 1, 2, n. Okay. Now there can be a situation that this guy wants to go to 1, this guy wants to go to 1, this guy wants to go to 2. So now what we are asking, what is being asked for you to assume that all of these jobs which wants to go to the same output port can virtually form a queue, right? So you can look at such a system because they are actually waiting to get served through this output port, right? So therefore there is a queue, a virtual queue for them. They are waiting to get a chance to get served to this output port. Okay, so you can assume that you have packet from this is from port 1, you have another packet for towards output port. So this is input port 1. Okay, let me write it as I1, so that there is no confusion. So this wants to go to the output port 1, it is from input port 1. This wants to go to output port 1, it is from input port n. Okay, so like that many other uh, packets or jobs can be there which would want to go to the same output port. Okay, and they're waiting for their chance to be get served or to get served. Okay, so this is the assumption that we are currently considering, that all the packets in the head of the line, so these should be in the head of the line. We are not considering packets which are later on in buffers. All the packets which are in the head of the line of the input ports, which want to go to the same output port, they can be assumed as if they are queued in the same virtual queue. This is a virtual queue. Okay, virtual queue for going to the same output port. Okay, I hope that this part is clear. Let me get to the all right. Now, now EBI. Okay, what was EBI for us? BI was the packets destined for output port I in a time slot that were not selected for transmission due to output contention. That means they are nothing but packets. Now, because you are assuming it to be, I mean, packets which are not selected for transmission due to output port contention, we are assuming them to be queued in the virtual queue. Okay, so they can be considered essentially as E of n queue. That means the average number of jobs that are waiting in the system until waiting in the queue until they can be served. Okay, now that is for the queue. Now here your switch has a fixed capacity. Okay, switch the that means how fast your switch fabric can transfer the packet. Let me just go to the diagram once more. Okay, so see your switch fabric, this is the switch fabric, it has a fixed capacity. Okay, then what else do we have? This is fixed. We have the fixed packet size, fixed packet length. So packet length is also fixed. Okay, so these two are fixed. So that means the server will take the fixed amount of time to serve these packets. Okay, now let us look at this system. You have a virtual queue where packets which are waiting in the head of the line of the input ports, they are forming a virtual queue. Your switch fabric, this is, let me call switch fabric. Okay, your switch fabric has a fixed capacity and the packet length is fixed. Okay, so now what does it become? In the arrivals, you do not have any control on the arrivals, right? So in general, for those kind of systems, we just assume that we are currently assuming that the inter-arrival time is following exponential distribution. So for that case, because why we are considering as exponential distribution, I gave you the example of waiting for taxi in front of an airport. Okay, that means whatever is happening at the current state, only that is going to affect the next state. Okay, whatever happened in the history, that is not of any concern. Okay, in the past, whatever has happened, that is not going to affect it. Okay, now with that example, please think of what happens in a network scenario. Okay, when you have a router. Okay, when you have a router, this is your router, right? This is your router. See, we show in a diagram that this is just a single line. All right, but there can be traffic that can come from several hosts to this guy. Okay, and how they are coming, that is coming from different users. Okay, different users from different devices, etc. Okay, and nobody has control on what the user wants. Okay, so because it depends on the will of the users, because it depends on what kind of applications the users are kind of using at that point of time, there is no control on that. Okay, so most of the times, so that means how the packets are getting you know, waiting or entering into that queue that is there in the router, how they are arriving, that will not depend on whatever has happened in the past. Okay, so that is the reason that in general, when we are looking at a router system, the inter-arrival distribution can be considered as exponential. That means it will have the memoryless property. Okay, so same concept we are using here. That is, we consider that the inter-arrival time distribution is exponential. So we consider that the arrival is basically having the memoryless property. Then we have already told that the switch fabric has fixed capacity, packet length is fixed. So server will serve for fixed amount of time only. Okay, so the service time distribution will be deterministic. Okay, and of course you have one server. The switch fabric is basically going to send the packet from the current input port to the corresponding output port. Okay, so now you can consider such a system as an MD1 queue. All right, so why this is an MD1 queue, I have explained it to you. I hope that it becomes clear to you. All right, so now let's get to the slide that we were looking at. Okay, all right, so if you know that this is an MD1 queue, then we already know about different properties of MD1 queue. We have already studied. So that means EBI becomes what is the average number of jobs that are there in the queue. In general, it is given by what? Rho square by twice of 1 minus rho. Here rho is what? Gamma 0. Gamma 0 is your switch utilization. So that can be used here to find out EBI, which is equal to gamma 0 square by twice of 1 minus gamma 0. Okay. So now from equation 8, what was equation 8? You had found out that EBI is equal to 1 minus gamma 0. Okay. So with this value, you just use equations 8 and 9 and equate them together. So you get this equation 10 and then you try to solve for gamma 0. So can anybody tell me what is the value of gamma 0? You can solve it for gamma 0, right? Please solve it for gamma 0 and find the value of gamma 0. Okay. So let me also do something with you so that I'm not bored. Okay, let me just. What are we trying to do here? 1 minus gamma 0 is equal to gamma 0 square divided by twice of 1 minus gamma 0. So what does it become? Gamma 0 square is equal to twice of 1 minus gamma 0 whole square. Then how do we do this further? Is equal to twice of 1 plus gamma 0 square minus twice gamma 0. Okay, now I think you guys can find out what is the value of gamma 0. Please tell me. What is the value of gamma 0 now?
Ma'am, it's 2 plus root 2 or 2 minus root 2.
2 minus root 2. What is the value? How did you get that?
Just by solving this equation.
What is the value of that 2 minus root 2? How are you getting? I mean, what is the value that you are getting 2 minus root 2?
So 2 minus 1.41, so it will be around 0.38 or 39.
Hmm. Can you just see this once again? How are you getting this value?
Let me recalculate, ma'am. I think it's correct, 0.38.
Mhm, mhm. No, the value is not correct, huh?
I'm 0.586.
How did you get it?
It's the same 2 minus root 2. It's just that the value he gave in the end was wrong. It's 0.58.
Hmm.
It's 2 minus root 2 only.
Okay. So, let me just do it a little further. Is everybody getting this? How am I finding this value out?
Yes, ma'am. 0.268.
No, 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 no. This point 0.5, somebody got 0.5, something 5. How much did you?
86.
586. No, that's the value. That's the correct value.
Yes, ma'am. 0.586.
0.586. Okay. So you will get 2 minus root 2 later on. I'm just not doing further calculations. Okay, somewhere you will get it. Okay. Otherwise I have to start with a new page. Okay, all right. So see, you get 0.586 here. So now we get to the conclusions of this part. We have seen for a bufferless switch, the maximum theoretical link utilization is 63%. Okay, whereas we were trying to find out the maximum theoretical link utilization for switch with having input buffer only, not having output buffer. Okay, so there you are getting approximately 58% or 58.6%, whatever decimal value you get later on. So 58% approximately you are getting the link utilization. Okay, so one might think, or you can only ask me that why is this happening? That if I am having no buffer, then I am having better link utilization than the scenario where I am having a buffer. Okay, which should be otherwise, because a buffer should, in general, a buffer should actually give you better values than a non-buffer kind of a scenario. Okay, so this question I am posing to you, please think on this. Okay, this is a very, you can think, just have some critical thinking in your mind, that a scenario where I do not have buffers, I'm getting more link utilization than the scenario where I do have buffers. And whereas essentially buffers are kept so that you have more utilization and you have less number of drops. Okay, so why is this coming out as this? Okay, so this is the question that I am putting for you guys for the next class. Whenever before the next class, I would like to ask you guys these questions. And now what we are going to see, okay, we are going to see the next part of this module. That means, first of all, if I have buffers, then how can I, buffers at the input ports, then how can I improve the quality of service or improve the switch utilization? And if I have output queuing, then in that case, how will it work out? Okay, how will I have a better scenario than that? Okay, so today's class, I would like you to give, or I would like to give you just some um, overview of what I'm going to do in the next courses. Now I will start a new page. Just let's go to a new page. All right. So today we are going to see some techniques which can be used to improve input queue switches. Okay. So just hold on a second. Okay, just a second. Hmm. So now, what can we do? Or how can we find out that we can uh, have such a system where we can still improve the the input queues, the quality of service of the input queues. So what was happening until now? Okay, so you have input. These are just input port buffers. So what was happening that you can have one packet that goes to output port 1, another that goes to 2, then again to 2, then to 1 again, then again to suppose 3. Okay, so in those cases what would happen, that there are other guys which probably can go to some other port, okay, but they are getting blocked because of all of these guys which are in front. Okay, so what we are going to do now, how can we improve such a system? Okay, so instead of having like one buffer from where you take out the jobs in a, so we are simply using FCFS at this point of time. That means one by one you are taking out the packets. Okay, so because of that, what's happening, they are the other packets which could have gone, which could have got the path, they are also waiting because of head of line blocking, right? That is what was happening until now. So instead of going through all of that issue right now, we try to put many more buffers at the same input port. Okay, so that is known as virtual output queuing. Okay, so what we do is, suppose this is input port number 1. Okay, this is input port number 1. Now you have, suppose, some n number of output ports. I'm not writing all of the n buffers here. I'm just making like 2 or 3 buffers, how much ever fits here. Okay, so these are some virtual buffers that I am putting at the same output input port, sorry, same input port. So that means what? Now your arbiter will come into picture. That means your scheduler. Okay, now it will be the task of the scheduler to now check that which one of these, so what we were having in input port 1 earlier, 1 and 3. So this is, this one is corresponding to output port 1. That means all the packets that want to go to output port 1 and they are arriving at input port 1, they will be queued here. All the packets that want to go to output port 2 and are arriving at input port 1, they will be queued here at this place, at this queue. All the packets that want to go to output port 3 and are arriving at input port 1, they will be going to this virtual output queue. So here we will have a packet with 1, here you will have a packet with 3. Okay, like I'm just putting these values here, 1 and 3. It is very small, I know. So this is 3 and this is 1. Okay, so here you have a packet that wants to go to output port 1, here you have a packet that wants to go to output port 3. Okay, so now just a second. So now any packet that arrives here, now the arbiter will check. Okay, the arbiter will check that whether there is a packet that is in contention with other output ports, or there is a packet that can be sent via this input port to the corresponding output port, even though there are other packets that are in contention. So it will leave the packets that are in contention and it will send the packets that are free and that can be sent through this link to the corresponding output port. Okay, is this clear? Is this clear somewhat? Otherwise, I will again, of course, explain it to you in the next class once again. Today we are out of time, but please remember this concept which is known as virtual output queuing or VOQ. Okay, this is a very efficient way of increasing the switch utilization even when you have buffers at the input ports. Okay, it can sometimes give 100% of utilization. Okay, but yeah, it's not always true. It theoretically it can give, but of course we know that it cannot be true always. There must be some issues that also we are going to study in the next classes. Okay, so this ends today's class, and if you guys have any question you can ask me. Otherwise I will stop today's class and then we will start